In this video, we want to talk about sample mean and sample variance, and these two concepts, they may be, you may face and need these if you want to do a little bit of statistics. So in this example, we consider the sample mean and sample variance of a normal IID sequence. So basically, we assume that x1, x2, xn, they are independent and they have identically normal distribution. So and then we take the sample mean. This is sample mean, and this is sample variance. We define it like that. Remember that we put n-1, and there is a reason for it, because this x bar is itself is a function of xi. So if you don't put n-1, then you will fall in trouble. For instance, you can consider these for case of n equal 2. If you have n equal 2, x bar is equal to x1 plus x2 divided by 2, and then you will have x1 minus x1 plus x2 divided by 2, and then to the power 2 plus x2 minus x1 plus x2 to the power of divided by 2 to the power of 2, and then divided by something. Okay, what I mean is that this guy becomes x1 minus x2 divided by 2 to the power of 2, and this guy also becomes x1 minus x2 divided by 2 to the power of 2. So you need to divide these by n-1. If you divide it by 2, is going to be different as opposed to divided by 1. So what I mean is that we divide it by 1, which is 2 minus 1. You see, so we want to prove that these two random variables are independent, and the proof is easy. So first, we know that a simple but interesting fact, and the fact is that the basic property of the covariance is that these x bar from these x bar is that xi minus x bar are uncorrelated. Okay, so try to do this one. So how you do it is that you say x bar times xi minus x bar, okay, and expected value of this one. So is equal to what? Mean of x bar xi minus mean of x bar to the power 2, etc. And then you show that this is equal to 0. Now, so consider that you have n random variable, and then I convert these n random variables to x bar. So this is the first one, second one, etc. So I transform. So you have what? I have x1, xn, okay, and then I put a transformation here. The first one is x bar. The second one is the difference between x1 minus x bar, etc. And the last one is xn minus 1 minus x bar. So the deviation of your random variables. I do not consider the deviation of x of n minus x bar, because in that case I will have n plus 1 random variables as opposed to n random variables. What happens is that if you eliminate the last one, you will have a system with n inputs and n outputs. Okay, so here I eliminate the last one. So this is a linear transformation. And interestingly, the components of the outputs are uncorrelated with each other. And interestingly, the mean of the first component is equal to the mean of your random variables, and the mean of others are equal to 0. And because they are the inputs are jointly and your transformation is linear, the outputs are also jointly normal, and because they are uncorrelated, they also are independent. So, so here I could easily see that these guys are the deviations from the center, from the sample mean, are uncorrelated with the sample means, and then they are uncorrelated with each other. So this new transform vector is normally distributed. So this new vector of the deviations and the sample mean, they have a joint normal distribution. So so obviously you can see that if you consider the term that I have eliminated, if I add all the previous deviations together, this will give you the deviation of the last one. So the last one is linearly dependent on the previous deviations, and this is why we omitted that. And this is why when we define the sample variance, we say sum of squared of these one divided by n-1, because basically we have n-1 independent random variable. The last one depends on previous one and it shall be omitted, and this is why we have n-1. So this means that the sample variance can be written as a function of these d. So so basically, if you write summation of the last term is a function of the previous ones. So we can easily, based on the arguments that I've talked to you and explained here, is the sample mean and the vector d have a joint multivariate normal distribution because of this linear transformation. If you have a normally distributed random vector and if you have a linear transformation, the output should have a normal distribution. And the sample mean and the vector d should be independent. We said that x of d is independent of d, but also variance is a function of only d. Okay, so therefore a function of d should be also independent of x, because d itself is independent of x bar. So the proof is complete, and the distribution. Now the question is that what is the distribution of? So far we have concluded that x bar, sample mean, and sample variance are independent. Now, what is the distribution of x bar and what is the distribution of v bar? So obviously we said that x bar has a normal distribution, but v bar we haven't said it. And we said that v bar is some squared of independent normally distributed random variables, because different deviations are independent of each other. The entries of vector d are independent. So if they are normal, same distribution, mean of 0, and sum of their squared, so it should have a chi-square distribution. So it's kind of like obvious. So moreover, from this expression, if you write it, you can get this equation, and then you can manipulate it, and you can easily show that the sample variance, if you multiply it by this guy, will become equal to this one. So it's sum squared of the deviation of random variables. So therefore, it should have a chi-square distribution of degree n-1.